Hello again and welcome back to physics. We're going to be looking at continuous flow today, so applying our knowledge of specific heat capacity and specific latent heat to situations that involve continuous flow. So you might be thinking to yourself, what is continuous flow? Well, that continuous bit just means at a constant rate, and the flow bit can actually refer to a number of different things. We can talk about a flow of energy or power. Or we could actually talk about the flow of a substance. So we could talk about, say, water going through a heater or a boiler or a radiator. And that can either be given to us as a mass per unit time or a volume per unit time. Now, if you are ever uncertain on these, just take a look at the units and try to mash the units together so that the units work. And chances are, if you can mash the units together and they work, then what you're doing is working. But we're going to go through the actual physics of it today. But that is a fallback, so that if you are in an exam and you completely forget about this, mash units together, it'll work. We have already dealt with the constant energy supply and changing temperature when we looked at our changing temperature example 3, where we're given the power rating of the kettle, we're given the efficiency of the kettle, we calculated how much power went into heating the water, and then we calculated for that amount of time how much energy went into heating the water, and then we calculated the temperature increase. So we went through quite a few steps in order to do that, and that's absolutely fine. Alternatively, we could combine those equations so that we could do it in one go. And when we talk about the other types of flow, so a flow of mass or a flow of volume, it's a lot easier if we combine our equations together. So to start with, we're going to take a look at if we're given the rate of mass flow, so something in mass per second of the amount of water flowing through a boiler, and that would have units mass per second of mass per unit time would have units of kilograms per second. So I'd like you to take a moment to try to work through that. Pause the video, and if you're getting stuck, play the video and it'll sort of give you hints and go step by step. So the first thing we need is the definition of power. See if you can remember that one. We should have P equals E over T, where P is power, E is energy, and T is time. And then we want to combine that with the specific heat capacity equation. Now, if you don't remember, that's Q equals mc delta theta, where Q is the heat added to the system, or the energy added to the system. M is the mass, C is the specific heat capacity, and delta theta is the change in temperature. And pause the video now if you haven't got those two combined already. So your combined equation should look like this: P equals mc delta theta all over T. This E for energy is just that Q, it is energy. And then we're going to rearrange it to this format, which looks a little silly, but really it helps us understand. So P is the power, M over T is the mass per unit time flowing through the system in kilogram per second. Now that is a mass flow rate or a mass rate that's going through that system. And sometimes you're actually just given that number instead of mass or instead of time. And you should treat it as M over T and not take T to be 1 second or anything silly like that. If you're given something in the units of kilogram per second, that is the mass per unit time flowing. And that is both of those symbols together. That would be the entire thing in brackets, M over T. C is our specific heat capacity, and delta theta is our change in temperature. Remembering that that could be in degrees Celsius or Kelvin because of the way that change works. And sometimes instead of a mass flow rate, you're given a volume flow rate, which would be meters cubed per second. So pause the video now and have a go at trying to get an equation that corresponds to a volume flow rate. So we're going to cheat just a little bit, and we're going to use the expression that we already had for our mass flow rate and just incorporate the relationship between volume and mass. If you don't remember, the relationship between volume and mass is rho, or density, equals mass over volume. We can rearrange that for M and then substitute it into our previous expression. If you haven't tried that, pause the video and give it a try now. So there's our previous expression: power equals mass rate times specific heat capacity times the change in temperature. And plugging in mass is density times volume gives us that expression. But notice that we want the volume rate and not the density volume rate. So again, we just need to separate out that fraction and sort of write it in this weird format. So just like before, that capital P is pressure, the rho is density, C is specific heat capacity, and delta theta is our change in temperature in degrees Celsius or Kelvin because it is a change in temperature. This entire term here, V over T, we treat as if it's one variable as opposed to the two variables there, and that is the volume per unit time flowing through our system in meters cubed per second. So we're going to try a question together. What I'd like you to do is pause the video and give this question a try. I'd recommend trying all three parts in one go, but when we go through the solutions, we'll go through part A and then part B and then part C. So if you want to go through the first part, pause it, check the answer, go through the second part, pause it, check the answer, you can do that as well. So pause the video now and give that a try. Alright, so this question reads, in a power station, water is heated in a boiler to create steam. This steam is passed through a turbine before being cooled by river water to condense it back into the liquid state. The cooled water is then pumped back to the boiler for reuse. The cooling water enters the condenser at 16 degrees Celsius and is returned to the river at 40 degrees Celsius. So if we want, we could calculate our change in temperature here by going final minus initial, or 40 minus 16, which gives us 24. Every second, 35 times 10 to the 3 kilograms of water are removed from the river. Now we need to be careful with this phrasing. So every second, that amount of water is removed. And that is a mass. So this is actually telling us a mass rate. It's telling us a mass per second. So we've got 35 times 10 to the 3 kilograms per second, because that's every second. And then it says, calculate the power required to heat this water. The specific heat capacity of water, C, is 4,200 joules per kilogram per Kelvin. So we want to start with our power equation, because they've asked us to calculate the power. So they're asking us, what is this? So power is energy per unit time. And we want to combine this with our Q equals mc delta theta, because we are changing the temperature. And that is what the energy required is. So we've got power is equal to mc delta theta over time. Now we need to be a bit careful about this. We should not be putting in 1 second. Mathematically, if you put in 1 second, it'll work, but that's not equivalent to what the situation is doing or what's happening in the situation. So if you put in 1 second, you're saying this happens in 1 second, and you're almost saying the only thing that happens takes 1 second. You're sort of implying that the time doesn't happen afterwards, or that after a second, this process is done. Sort of like if you were to do a practical and it takes you 10 minutes, right? You'd put in time as 10 minutes and that would be the end of it. So we do want to emphasize that we realize this is a rate, this is a continuous thing, this is a thing that continues to happen over and over and over again, by showing that we understand that this is a rate, this is a mass per unit time, and not that we're just going to look at 1 second. So then we could plug our numbers in, and we've got power equals our rate, which is 35 times 10 to the 3 kilograms per second, times our specific heat capacity of 4,200 joules per kilogram per Kelvin, times by our change in temperature of 24 degrees Celsius. Notice that it's a change in temperature, so this degrees Celsius is also equivalent to 24 Kelvin because it's a change in temperature. Also notice that I've done a substitution here of a change in temperature straight into one number. If you still have these two numbers, you should show this calculation inside your substitution. So it should look like delta theta, and the next line should be theta f minus theta I, and the next line should be 40 minus 16, so that you are showing that substitution. One variable turns into one number. and not a bunch of numbers or a sum. And then we plug this into our calculator and we get P equals 3.53 times 10 to the 9 watts. Now this is a past paper question and you get 1 mark for showing this substitution and 1 mark for the correct final answer. Notice that for showing substitutions you need to actually show your equation and how things go into it. So m over t, that's where that goes. C, that's where that goes. Delta theta, that's where that goes. And really, if you put 35 times 10 to the 3 over 1, you would technically lose out on the substitution mark because it's not happening in 1 second. That happens every second. Now, if you haven't done question B already, pause the video, give it a try. So part B, assume that all the energy transferred by the river water came from steam changing to water without a change in temperature. Calculate the mass of steam passing through the turbine per second. So again, they're asking us for the mass per second. They're asking us for that rate. And then it gives us the specific latent heat of vaporization of water as 2.4 times 10 to the 6 joules per kilogram. And so that's going to be our specific latent heat of vaporization. Now this also requires us to use our answer from part A, where the power was 3.53 times 10 to the 9 watts. And we're going to use our definition for power, energy per unit time. But this time the energy isn't due to a change in temperature, the energy is due to a state change. And our equation for energy due to state change is Q equals mL. So we're going to plug that into our equation instead, and we get P equals mL over T. Remember, it's this m over t that we want, so we're going to rearrange for m over t, which gives us P over L. And then we can just substitute our numbers in. So our mass rate, or the mass per second, is 3.53 times 10 to the 9 watts all over the specific latent heat of water, which is 2.4 times 10 to the 6 joules per kilogram. And plugging that into our calculator gives us a mass rate of 1.47 times 10 to the 3 kilograms per second. So the marks for this one are 1 for the substitution and 1 for the correct final answer. 2. If you haven't done question C, pause the video and try question C. The turbine is linked to a generator that produces 800 megawatts of electrical power. Calculate the efficiency of conversion of the internal energy of the steam into electrical energy. So we're asked to calculate efficiency, which is a really long word and doesn't have a technical short in the equations. So we'll just leave it as efficiency, and that is our useful energy output over our total energy. And this is often written as input, but it doesn't really matter if you write it as input or output because energy can't be destroyed, only converted from one to the other. So these energies, I mean, we could talk about efficiency in terms of energy, but we could also talk about efficiency in terms of power. Now, technically, the reason for this is we kind of multiply it by a sneaky little fraction that's just 1, right? Multiplying time by time. But then, you know, that gives rise to having energy per unit time over energy per unit time, and energy per unit time is actually power. So rather than writing energy, we can write power. And now here's where you might make a mistake. This is the tricky bit. The useful power is the electrical energy that comes out. So that's the 800 megawatts. The total power is the bit that you might be a bit mistaken on. So the total power, well, we get that 800 megawatts out, and we also get the energy that's wasted in terms of heating the river water, or our previous answer of 3.53 times 10 to the 9 watts. And, you know, I have to do a little bit of unit conversion to get this to work. 800 megawatts is 800 times 10 to the 6 watts. And adding these together gives us 4.33 times 10 to the 9 watts. And then we can substitute that into our efficiency equation. So we've got our useful power over our total power, and just plug our numbers in. So useful, that's 800 megawatts, or 8 times 10 to the 6, or sorry, 800 times 10 to the 6, or 8 times 10 to the 8 watts, over 4.33 times 10 to the 9. Plugging that into our calculator, we get 0.185. Now, if that's the version of efficiency that you use, that's a completely correct answer. If you do have the multiply by 100% efficiency and you prefer to use that, that's fine as well. You'll just end up with an answer of 18.5%. Now, it doesn't matter which one is your final answer, 0.185 or 18.5%. Just don't get the units confused. If you're going to have 0.185, there is no units there, no percentage. If you're going to have 18.5, you need the percent sign. And in terms of where these marks actually come from, you get a mark for recognizing what the useful power output is, and a mark for the correct final answer. And it doesn't matter if it's this answer or this answer, correct final answer gives you a mark. So the key concepts from here. Whenever you're given a flow rate, combine your heat equations with the definition of power, or P equals E over T. Group the per unit time bit with the appropriate variable, so whether that's mass or volume, make it one variable, so you've got mass per unit time or you've got volume per unit time. And to tell if you've been given a flow rate question, check your units. You should have a power and you should have a mass rate, which is kilograms per second, or a volume rate, which is meters cubed per second. So either you should have both of those pieces of information, or you should have one and they should be asking you for the other. And if you're really stuck, just use units. Have a look and go, right, kilograms per second, what can I multiply that by to get a power, and work through units that way. So hopefully that helps you with continuous flow problems. Have a fantastic day.